So this video is covering the last example from the notes for section 4.8 over Lagrange multipliers. So in this problem, we're trying to determine the dimensions of a rectangular box open at the top, having a volume of 32 cubic feet and requiring the least amount of material for its construction. So I was starting the problem by drawing a picture of this box. Notice it is open at the top. So we're going to label the three sides, X for length, Y for width, and Z for height. And let's first look at the description here. We are trying to find the dimensions. So we're trying to find the values of X, Y, and Z such that the volume is 32 cubic feet. So we know the volume is 32 cubic feet. This is our constraint. So our constraint is that the volume is 32 cubic feet. Now, volume for this problem is length times width times height because it's a rectangular box. In other words, it's X times Y times Z. So our constraint is G of X, comma Y, comma Z equals X, Y, Z minus 32 equals 0, right? So next, we need to figure out what we're maximizing or minimizing. Now, we'll notice I highlighted where it says requiring the least amount of material. So we're minimizing because we're requiring the least. Now it says amount of material for this construction, right? Now it's a rectangular box open at the top. The construction is the sides of this box. So we have 5 sides. In other words, we're trying to minimize the surface area of the open top box. So we construct this surface area function S of X, comma Y, comma Z. It's the area of the bottom plus the area of the front plus the area of the back plus the area of the left side plus the area of the right side. Now the front and the back are going to have the same dimensions. The left and the right sides are going to have the same dimensions. The bottom will be X times Y. The front as well as the back will be X times Z each. So we'll have 2 copies of those. The left side and the right side will be YZ and YZ respectively. So we'll have 2YZ. So in other words, what we're trying to do here is we are trying to minimize this surface area function S of X, comma Y, comma Z equals XY plus 2XZ plus 2YZ subject to the constraint XYZ equals 32, written as 0 equals G of X, comma Y, comma Z equals XYZ minus 32. So what we do is we take the partial of S with respect to X and set it equal to lambda times the partial of G with respect to X. So that's Y plus 2Z will equal lambda times YZ. We take the partial of S and G with respect to Y, and we multiply the partial of G with respect to Y by lambda. We get X plus 2Z equals lambda times XZ. Now we do the same thing, but with the partial with respect to Z, we'll get 2X plus 2Y equals lambda times XY. And we get the final, we also make sure we add the constraint, which is XYZ minus 32 equals 0, which we can also write as XYZ equals 32. Now notice what that tells us, this last part. X times Y times Z equals 32, so none of these values can be 0. They just can't be 0. So we know that. So there's a couple things we could do with this example. I like this example because it shows we have a couple different things that we can try to do to solve this. You know, we could divide the first equation by YZ. We know Y and we know Z are both not 0. So we could divide, solving for lambda. And then in the second equation, we could also solve for lambda. In the third equation, we could also solve for lambda. And then we could go ahead and set those 2 equations equal to each other at all times, respectively. But there's something else we could do. Notice that in this right-hand side, we have lambda times YZ in the first equation. Left-hand side of the second is lambda times XZ, and the third is lambda times XY. So if we multiply both sides of the first equation by X, we would have on the right lambda times X times Y times Z. And if we took the second equation and multiplied both sides by Y, we would get lambda times x times y times z. And then if we took the third one and we multiply both sides by z, we would get on the right side lambda times x times y times z. And so we know each of these are equal. So let's take the first and the third. On the left side, we get, if we multiply x through, we get x times y plus 2xz equals the right-hand side, which is lambda x, y, z. But this equals the left-hand side of the second equation, which is, once we distribute the y, xy plus 2yz. Now, notice both of these expressions have an xy in them, so we can subtract them off from both sides, and we'll be left with 2xz equals 2yz. And we know 2 and z are both non-zero, which tells us that x equals y. Now, we can also do this with the first and the third equation. So let's do that. Remember, once we distributed the x on the first equation, on the left side, we got xy plus 2xz, and on the right side, that equaled lambda xyz. But that equals the right side of the third equation, which will equal, once we distribute the z, 2xz plus 2yz. Now, notice both of these have a 2xz in them, so we can subtract them off from both sides, and that would give us xy equals 2yz. Now, we can divide both sides by y and get x equals 2z. So we know x equals y and x equals 2z, or in other words, z equals 1/2 x. So that tells us that 32, which equals x times y times z, will equal x times y, but y equals x, times z, which is 1/2 x, which all together, when we multiply them together, is 1/2 x cubed. In other words, x cubed equals 32 times 2, which is 64. And so x is going to be the cubed root of 64, which is 4. Okay? So that tells us then that y will equal 4, and z will equal 1/2 times x, or in other words, 1/2 times 4, which is 2. And all those units are feet, because our units up above were cubic feet. Now, this problem doesn't ask you to find the amount of material that's needed, but we could do that. We could replace x with 4, y with 4, and z with 2. We'd get 4 times 4 plus 2 times 4 times 2 plus 2 times 4 times 2, which is 16 plus 16 plus 16, or in other words, 48, and that's going to be square feet. You can also use this fact to verify that the dimensions that minimize the area are 4 feet by 4 feet by 2 feet by, trying a different set of values that would give you a volume of 32. For example, x equals 1, y equals 1, z equals 32. If you plug that in, you get 1 times 1 plus 2 times 1 times 32 plus 2 times 1 times 32, which is obviously a lot larger than 48 square feet.